Okay, so welcome everyone. I'm Hiroki chairing this session. So today we have 6 talks in this session. Each talk going to be 20 minutes long. So please feel free to keep posting your question to the chat, or if we have the additional time for the verbal Q&A, you can also raise a hand. Okay. Without further ado, the first presenter, Paolo Sibani and Steen Rasmussen. Go ahead.
Okay. Thank you very much for this opportunity to present our work. So let me just start without further ado. The theme of this talk is human wealth development over history and the fact that it is an accelerating stage process. So how do I identify stage and what are the events marking its beginning and the end? I'll give you some introductory example concerning decelerating optimization processes from physics and paleobiology. And then I'll turn to evolutionary expansion, which is an accelerating process, and present the hypothesis that finite time singularities represent the endpoints for an accelerating evolutionary expansion. And then that is, of course, what you're looking at is human wealth growth as an example. Okay, so here are some take-home points. Then you can forget the rest of the talk. So the first one is that the natural variable to describe to wealth growth is not usual Walker time, but is this intensity. The intensity of human interactions, which we call tau. You can see that, you will see that evolution is staged. There are different stages characterized by different exponential growth as a function of this current time. And the important thing is part of the wealth which is produced goes into improving the intensity of human interactions. So that creates a positive feedback loop, which leads to a finite time singularity in our wealth. And the final point is, do we have to mend our way? Because of course, to avoid, or the system will change. So that will of course not happen. Okay, so there are a few basic references and all the references in there, and I will not give you many references in this talk because there is no time for that. So I'll just let you look at those. This is the first one is about record dynamics. I mean, how to describe statistically these state processes. The second is with Steen. 2 modes of evolution, optimization and expansion, which we referred to. Then there is this human wealth evolution, trends and fluctuations. And then there is these these Alive 2021 proceedings, which is basically the starting point for this talk. Okay. So let me first give you 2 examples of a decelerating optimization process, and they are from physics and paleobiology. The first one concerned with the number of vortices in a model, so it's a computational model of ITC type 2 superconductor. And this is a work of Oliveira et al., which is given, you can look it up in Physical Review B. And the point is that this number of vortices grows logarithmically, but it's a stage process, and you say it's a stair in log time. The second example has something to do with evolutionary biology. It's an analysis by Newman and Eble, which looked at the accumulated number of extinction events in marine families extinctions, and they used the data of Rapp and Sapkowski from 1982. In this case, extinction rate decelerates as 1 or t. That means the total number of extinction grows as log t. And there is an initial event, which is the Cambrian explosion. Okay, let's look at the first picture. It's just a picture. You don't need to know much about the details, but just notice the fact that the abscissa is logarithmic and that you have basically the trend is a straight line. So you have a logarithmic growth. So that is what the point already did. You have all these plateaus, and there are events which bring the system from one plateau to the other. The second example, there is a fit. So there's a data, and the fit is a logarithmic fit. That's the formula. The important thing is that there is an initial time, which is explicitly given, and the initial time is the time of the Cambrian explosion, minus 262 million years. And of course, the extinction rate decelerates as 1 over t. That's exactly the same as in the other example. So these are data. You can see that looks pretty good. You have a linear line basically on when the abscissa is logarithmic. Yes. Okay. So let's now turn on our GDP data. So we use gross domestic product as a proxy for cultural evolution. It's given per capita, and it just measures the activities which are carried out by humans, and they're based on the infrastructures and the institutions that sort of maintain a population that has some shared cultural values. And of course, some social and technological know-how, which are the basis for the whole thing. So basically, looking at GDP history gives you some information about how human culture evolves in time. And there are long time series, well, relatively long time series, and this is the reference of all in data. Okay, so let me give you my first example. That is the UK wealth. So what is this wealth? This is the GDP, which is scaled by its initial value. So the initial value is always 1 because it's scaled out. And you can see that if you look at this data, or this plot, you can see there are red, the red data, these are the data. And then there are these yellow circles. So you can see between two yellow circles, there is a line, and this is an exponential fit to the data in that stretch. So basically, you fit your data by a series of exponentials. What you see in the insert, that's the deviation from the trend. So that is the, oops, sorry. That's all web data. So let's then look at an average trend model. So there is no modeling, if you want, it's just a fit of data. Now we want to make a model and model the GDP trend by an ordinary differential equation, or ODE. Sorry, this one here. So, and this is the point I already gave you to you is that increasing intense communication, that's the reason why, our collaboration, our human collaboration increases, and that is beyond this increase of GDP growth. Okay, so we don't use at first, we don't use the Walcott time as a natural variable, but we use this other variable, tau, which measure this intensity of the interaction. And in terms of this variable, the wealth grows in a way which is very simple. It's basically exponential. Actually, it's linear for short times, but exponential for longer time. So it's simply exponential. So you have a series of exponentials. That was the data I already showed you. Okay. So now we want to turn from this natural time to Walcott time. You have to connect the one to the other. And this is the connection. dt tau is proportional to the wealth itself. that if you do the math, which is relatively simple, then you can see that, first of all, that if the wealth is constant, T and tau are simply proportional. But if the wealth grows, they're not proportional. And in fact, you get a differential equation, which has a finite time singularity. That's, I give you the solution. That's the solution. So this is the wealth as a function of wall clock time. It has a finite time singularity, which I call T star. And if you then look at the data, then this finite singularity is about, I don't know, around 2020, 25. I mean, it's very close if you want. So these are the data with the analytic fit. So this is still the UK data. And then maybe, I don't know if you can see, there is a red line, and the red line is the fit. And what you see in the insert, that's the deviation from the trend. So that's the okay. So that's what happened? Sorry. Here we go. So of course, we know that finite time singularities do not happen in reality. So we are not going to be infinitely rich, even though some people are trying really hard to do exactly that. But so what our analysis suggests is that the big changes will soon happen. So we have to, in our values and the way we interact. So that's as we have seen that, we've seen in many cases that change in interaction patterns, so they start so-called aging processes in glassy system. And that's the same, I think, which is going to happen in our case. So to check how that happens, one should do more simulation, of course, and elucidate how systems get through these critical points. What happens? Of course, we are not able to, we can try it out. I mean, just live through it and see what happens. In any case, I think that concludes my talk. Thank you for your attention. And then we have 5 minutes for question and discussion, if you like. Thank you.
Thank you very much. Very interesting work. And we have plenty of time for discussion. So now the floor is open for anybody to ask questions. I have a couple of questions, but let me first invite the audience to feel free to unmute and ask any questions.
See what the questions are.
Yeah, let's see. There is a question.
Okay. From Sina. Yeah. Could you expand on start aging process in glassy systems? Yeah, this is a technical word. Could you elaborate more what this means?
Yeah. Okay. So in many glassy systems, they could be spin glasses. It could be, well, that's the example I gave you, high TC superconductors. You start an aging process by doing something to the parameters of the system. Typically, for instance, you could decrease the temperature below a critical point, and then you just dump your system into a critical region, and then the aging process starts. What is an aging process? That's a process where, if you look at average quantities, so average observables, they appear to be constant for a while, and then they jump. So it's a stage process. Of course, if you have a system which is composed of many subsystems, then the thing smoothens out. So actually what you observe is a very slow and decelerating change of your average variables. So, I could speak for hours about aging processes, but of course I don't want to do that. The question is now, is this sort of, would that answer the question? Is that enough, or do you want to know more? Because there is much to say about aging systems.
Yeah. So Sina also posted a follow-up question. So is this related to the same as critical slowing down?
No, it's not. Critical slowing down is something which happens when you are at a critical point or near a critical point. we are not near a critical point. We might be near, but we are below a critical point. So in an aging system, you never reach equilibrium. So you're striving to reach equilibrium, but the time it takes is longer than your life. So basically, you never get there. So it's different.
Yeah. Thank you. We can take several more questions. I have one question, maybe two. Yeah. So whenever physics tells us that the singularity or divergence to infinity, there's always another limitation from the other type of physical laws kicks in, so that the system actually never diverges, right? So in this case, exactly. I guess what are the other constraints? Could be the human cognitive ability, or could be the energy limit. So do you have any explanation?
Yeah. Thank you. That's a very good question. So of course we'll not see a divergence. Exactly right. But so what will happen is that other mechanisms would kick in. So let's see. Let's put it this way. You have a simple theory. It works very well for 800 years, and now you know that within the next 10 years or so, it's gonna fail dramatically. Mm-hmm. Then you know that the sort of the assumption that you put into this theory, they will turn out to be wrong. There is something new will happen.
Yeah.
So of course, and then you can of course go into the details, say what could it be? It could be many things. I mean, basically, if I just say put it very shortly, we have reached the limit. We now we have our little globe. We have filled it up and we cannot expand any longer. That's one way to put it. In any case, what I think is interesting is that you can see this behavior just by looking at economic data. Even if you look at economic data, you stop your analysis in 1780, I think that was about 1780. So we just cut off the last 250 years of data, then you see that it will be a critical point more or less at the same time. So this critical behavior is inherent in the way we interact. So we have to change our interaction, or it's not a choice. Our interactions will have to change in order to avoid this singularity, which of course will not happen. I don't know, does that answer your question?
Yeah, yes, sort of. But there are also the more practical things that we can list. For example, like a human biology or physiology could be one limiting factor, right? Because no one can process infinite amount of information in one day.
Yeah, absolutely.
Or maybe the energy crisis would be yet another. There are what would be the most most meaningful limiting factor that first kicks in to break this singularity prediction? So that was my question.
Yeah. Well, I mean, I think the one you mentioned yourself, that is something which I also thought about, is that people are not able to process. I mean, there is a natural limit to how dense interaction you can have. Mm-hmm. At some point, you are fed up with interaction. You want to just sit down and watch TV or something like that. And that, I think, will be the first thing which will happen.
Yeah, I agree, totally agree. Any other quick questions? If not, thank you very much, Paolo and Steen. Really interesting work.
Thank you very much.